Here's a tough problem. If you keep flipping a coin, what's the probability that at some point the number of tails will exceed twice the number of heads? In this video, I'll show you how to solve that problem and others by drawing a picture called a state diagram. State diagrams are simple enough to be explained in a minute, but powerful enough to solve problems that look out of reach. We'll start with an easy warm-up, build up the idea step by step, and finally tackle that coin flipping problem. Are you ready? Let's go! Here's a warm-up problem. We have a standard die with 6 sides. We keep rolling it until we get a 6. On average, how many rolls are needed? You may already know the answer, in which case, great. I'll describe a particular method to solve it, which we'll use throughout this video. We'll draw a picture. Start with a circle. Then we'll roll the die for the first time. If it's a 6, then we can stop. If it's a 1 through 5, then we haven't made progress, so we're back at the start. We're really interested in probabilities. What's the probability that we get a 6 on the first roll? It's 1/6, so we can relabel the arrows like this. Each circle is called a state. The entire picture is called a state diagram. We'll begin at the start state and keep following the arrows until we reach the stop state. How many steps will that take us on average? We'll give a name to that average time, call it A. I'll place an A in the diagram, just below the start state. We'll come up with an equation for A. At a minimum, we have at least one roll. If the first roll is a 6, then we have no other rolls. So 1/6 of the time, we have 0 other rolls. If the first roll is not a 6, then on average, we have A rolls after the first to get a 6. So 5/6 of the time, we have A extra rolls on average. That gives us the equation you see here. Now we can solve. The 0 goes away. We can combine the two terms with an A. We find that A is 6. The average number of steps, the average number of rolls is 6. Next, let's try a problem where we don't stop after one success. We'll collect multiple successes. Again, we keep rolling a die. This time we want to eventually roll each of the 6 numbers at least once. On average, how many rolls are needed? This problem is known as a coupon collector's problem. Imagine that a cereal company places a coupon in each cereal box. There might be 6 types of coupons, or 8 types, or more generally, N types. You have to collect every type of coupon to win a prize. On average, how many cereal boxes must you buy? The coupon collector's problem was first posed and solved by Demoivre in 1708. Back to our die rolling problem, which is a special kind of coupon collector. On average, how many rolls do you need to get all 6 numbers? Take a guess. To solve, let's draw a state diagram. At the start, our first roll is guaranteed to be a new number, so with probability 1, we move to a new state. I'll call the new state 5, since there are 5 numbers remaining. Okay, say we're at state 5. Most of the time, 5/6 of the time, we'll get a new number, so we can move to state 4. 1/6 of the time, we'll stay where we are at state 5. Now let's look at state 4. Remember, state 4 means 4 numbers are still missing. 4/6 of the time, we'll get a new number. 2/6 of the time, we'll stay where we are. I could simplify these fractions, but leaving them this way makes the pattern easier to see. In fact, let me rewrite the 1 on the left as 6/6 so the pattern pops out. By now, you see the entire pattern. I'll complete the diagram. We want to find the average number of steps from the start to the stop state. Again, I'll call that A and place it under the start state. But now we'll need other variables. For example, B will be the average time to go from state 5 to stop. Similarly for C, D, E, and F. A state diagram breaks a probability problem into 2 tasks. First, draw the diagram, and then write an equation for each variable. We have 6 variables to solve for. Where shall we begin? Every state points to the right, so the cleanest place to begin is at the rightmost variable, namely F. Here, F is the average time it takes to go from state 1 to stop. If you stare at state 1 and the stop state, that part of the diagram looks just like our warm-up problem. So we get this equation for F. We can solve for it just as we did in our first problem. We see that F is 6. Now let's solve for E. From state 2, we can go to state 1 or stay where we are. So we get this equation for E. We can solve for E like this. We find that E is 6 plus 6 halves. I could simplify that expression, it's 9, but the pattern is clearer this way. Okay, now we'll solve for D. From state 3, we can go to state 2 or stay where we are. So we get this equation for D. Let's solve that equation. We get this nice expression. 6 plus 6 halves plus 6 thirds. That's 11. At this point, the pattern is clear. By using the same process, we find the value for C and B, finally A. When we compute that final expression, we get 14.7. 14.7 rolls on average. The same method would generalize if we had n things to collect instead of just 6. So far, we've computed the average number of steps. Next, let's switch gears to find a probability instead. This game has 2 players, Alice and Bob. The game involves a penny or some other coin. We'll keep flipping the coin. Alice is looking for the pattern heads, tails, heads. 3 coin flips in a row with that pattern. Bob is looking for the pattern heads, heads, heads. We'll keep flipping the coin until Alice's pattern or Bob's pattern appears on 3 consecutive flips. What's the probability that Alice's pattern appears first? This is the famous Penney-Ante game, named for its creator, Walter Penney, who introduced the game in 1969. His last name is perfect for this game. Back to the problem. If you flip a coin 3 times, the probability that you get heads, tails, heads is 1/8. The same is true for heads, heads, heads. Both patterns are equally likely. So make a prediction for who has the advantage, Alice or Bob. They each win half the time, right? Wrong. Let's draw a state diagram to find the correct answer. I encourage you to draw your own state diagram. For example, what states will you need? Where shall you draw the transition arrows? Feel free to pause the video. Okay, I'll draw a diagram. How can Alice win? She'll need a heads, followed by a tails, followed by a heads. Going back to the start, how can Bob win? He'll need a heads, which we already have a state for. From there, he'll need a second heads, followed by a third heads. We still need to fill in some of the other arrows. For example, at the start, if we get a tails, we'll just stay where we are. Next, look at state HT. If we get a tails, where shall we go? We'll go back to the start. Finally, look at state HH. If we get a tails, should we go back to the start? No! Our last 3 flips were HHT. That means our last 2 flips were HT. So we should draw an arrow to HT. That completes the diagram. What matters are the probabilities, so let's change every arrow to show probability 1/2. We want the probability that Alice wins beginning from the start state. Let's call that A. I've placed an A under the start state. Similarly, we can place variables under the other states. For example, D is the probability that Alice wins starting from state HT. With this diagram in place, the equations write themselves. Where shall we begin? Different choices work. I'll choose to express every variable in terms of A. For that idea, it's best to start with D. Look at state HT. From there, we'll go either to the state A wins or the start state. So we get this equation for D. The right side simplifies. Next, look at state HH. From there, we'll either go to the state B wins or the state HT. So we get this equation for C. Again, the right side simplifies. We can plug in the previous equation for D. We get this new expression for C. Let's remember those equations for C and D. Now look at state H. From there, we can go to state HH or state HT. So we get this equation for B. It expresses B in terms of C and D, so we get a simple formula for B. Let's remember that equation for B. Finally, let's look at the start state. From there, we can either stay where we are or go to state H. So we get this equation. Solving it, we see that A equals B. Let's plug in our equation for B. We can solve this equation for A. We find that A is 3/5, or 60%. Alice wins with probability 60%. Looking at the state diagram, now we see why Alice has the advantage. There is an arrow from HH to HT, which is 1 flip away from Alice winning. There's no arrow the other way around. By drawing the state diagram and doing a little algebra, we figured out the exact probability. Next, let's apply that same method to one of the oldest problems in probability. Alice and Bob are playing another game, this time for money. Alice has $3 while Bob has $4. A coin is flipped repeatedly. If the coin comes up heads, then Bob pays Alice $1. If the coin comes up tails, then Alice pays Bob $1. They keep playing until one of them has no money. What's the probability that Alice wins the game? This is the famous gambler's ruin problem, introduced by Pascal. In 1656, Pascal challenged Fermat to solve a similar problem. Fermat replied with the correct numerical answer. Back to the problem. Because Alice starts with fewer dollars, she presumably wins less than half the time, but what's her exact probability? Let's draw a state diagram. We'll draw it from Alice's perspective. She starts with $3. Every time the coin comes up heads, she gains $1 until she gets all $7. Every time the coin comes up tails, she loses $1 until she goes broke. Let's draw the remaining arrows. Heads to the right, tails to the left. What matters are the probabilities, so let's label each arrow with 1/2. As usual, assign a variable to every state except the end states. For example, A is the probability that Alice wins from state 1. Since Alice starts with $3, we want C, the probability that Alice wins from state 3. Now let's write the equations from the diagram. Where shall we begin? Again, it's best to begin at one of the ends. For example, look at state 1. From there we can go to Bob wins or state 2. So we get this equation. Let's solve for B. We find that B is twice A. Now let's look at state 2. From there we can go to states 1 or 3. So we get this equation. Let's solve for C. We get this equation. Plug in our previous equation for B. We find that C is 3 times A. Let's do one more. Look at state 3. We get this equation. Solve for D like this. Plug in our previous values for B and C. We find that D is 4 times A. By now you see the pattern. In the same way, E is 5 times A and F is 6 times A. We've expressed every variable in terms of A, but we still haven't solved for any of them. What state have we ignored? State 6, let's look at it. From there we can go to state 5 or Alice wins. So we get this equation. Plug in our expressions for E and F. Now solve for A. So A is 1/7. We want C, which is 3 times A, or 3/7. The probability that Alice wins is 3/7, about 43%. As predicted, the answer is less than half, but now we know the exact probability. Would you like to see a slicker way to solve this problem? We'll use the same state diagram. Alice starts with $3. After one coin flip, she has either $2 or $4, so an average of $3. The game is fair. It's fair no matter how many times we flip the coin. In particular, at the end of the game, Alice will still have an average of $3. Here we're using a result called the optional stopping theorem. We're interested in the probability that Alice wins from the start. This time call it P. We'll place P under the Alice wins state to emphasize where we stop. The other end state is Bob wins, which happens with probability 1 minus P. We already computed the average number of dollars that Alice has at the end. Let's compute it in another way. With probability P, Alice has $7 and otherwise has $0. So here's the average amount that Alice has at the end. This expression simplifies to 7p. On the one hand, her average amount at the end is $3. On the other hand, it's $7p. Hence, 7p equals 3. That means p is 3/7, as before. That's a clever method, but not easy to come up with. So we can always use the previous method with a little more algebra. So far, every state diagram has been finite. Next, let's try a problem that requires an infinite number of states. The answer is surprisingly cool. I'll call this problem lopsided coin flips. We keep flipping a coin. What's the probability that at some point the number of tails is more than twice the number of heads? For example, if the first flip is tails, then we stop right away. Otherwise, if the first flip is heads, then we'll need at least 3 tails to stop. Maybe we'll never stop. This problem was posed by Donald Newman in 1959. Back to the problem. We stop if the number of tails exceeds twice the number of heads. We can rewrite that condition as an inequality like this. In other words, 2 times the number of heads minus the number of tails is negative. Let's look at the expression on the left. Every time there's a heads, the quantity goes up by 2. Every time there's a tails, the quantity goes down by 1. We can draw those movements on a state diagram. I encourage you to draw your own state diagram. How many states will you need? Feel free to pause the video. Okay, here's my diagram. Start at state 0. If we get a tails, we go down by 1 to state -1. That's the stop state. At the start, if we get a heads, we go up by 2 to state 2. We can fill in the rest of the state diagram. Each arrow is either 2 places to the right or 1 place to the left. The diagram continues forever to the right. This is our first diagram with an infinite number of states. What matters are the probabilities, so let's label each arrow with 1/2. We're looking for the probability that we reach the stop state starting from state 0. Let's call that probability A. We'll place it under state 0. Similarly, we can write a variable for every other state. For example, B is the probability of stopping from state 1. C is the probability of stopping from state 2. Let's look at probability B. We have to go from state 1 to state -1. To do so, we first go from state 1 to state 0, and then from state 0 to state -1. Both parts are 1 step left, so both have the same probability. Hence, the probability of eventually going from state 1 to state 0 is A, and the probability of eventually going from state 0 to state -1 is also A. Therefore, the compound probability B is A times A, or A squared. In the same way, C is equal to A times A times A, or A cubed. Let's remember those equations. We need one more equation to solve. Look at state 0, the start state. From there, we can go to the stop state or to state 2. So we get this equation. Let's clear fractions. We can replace C with A cubed. Bringing the terms to one side, we get this cubic equation. Do you see any solutions to this cubic? A equals 1 is one solution, hence we can factor out A minus 1. We get a quadratic. We can solve the quadratic with the quadratic formula. We get 3 possible values for A. Which of these 3 values is correct? We can eliminate one of them right away. Probabilities can't be negative, so we can eliminate the last choice. Remember that A is the probability that we reach the stop state from the start state. In other words, A is the probability that at some point the number of tails is more than twice the number of heads. We have 2 possible values for the probability. Which do you think is correct? The answer is not obvious. Why don't we run a computer simulation? Here's a little program I wrote. It keeps flipping a random coin until the number of tails exceeds twice the number of heads. I cheated a bit. Failure means that we never stop flipping coins, but my program can't run forever. So if the program ever flips 1,000,000 coins without success, then I declare failure. Here are the results. I ran 1,000 trials of this simulation. I tracked how often the program output success. Here's the graph over time. It looks like the success fraction is converging to just over 60%. Okay, let's go back to our previous work. The simulation suggests that 1 is not the answer. Let's look at our other value. The square root of 5 minus 1 all over 2 is about 0.618, about 62%. Let's give a name to that number. I'll call it psi, the Greek letter. Does this number look familiar? It's a cousin of the golden ratio. Remember, the golden ratio is the square root of 5 plus 1 over 2, about 1.618. Our number psi is the golden ratio minus 1. It's also 1 over the golden ratio. For that reason, it's sometimes called the small golden ratio. Where did we get psi in the first place? It came from this quadratic equation. That quadratic in turn came from this cubic. Let's remember that equation. Since psi is about 62%, it matches our computer simulation well, but we still need a proof that it's the answer. Let's head back to our state diagram. Each state is named after an integer, -1, 0, 1, 2, and so on. I'm going to rename the states after the powers of psi, like this. That seems like a weird thing to do. After all, changing names doesn't change the probabilities, but here's why I did so. Think of these names as representing how much money we have at each state. For example, at the start state, we have psi dollars, about 62 cents. Then we move left or right. After one coin flip, how much money do we expect to have? We have either psi cubed dollars, about 24 cents, or $1. So on average, we have this many dollars. That's a cubic. But by our previous cubic equation, that simplifies to just psi. In other words, we started with psi dollars, and after one coin flip, we still have psi dollars on average. It's a fair game. I chose the powers of psi to make the game fair at every state. We can keep flipping the coin. At the end, we still have psi dollars on average. I have to be careful when I say at the end, since the process might not stop. Again, I'll cut off the process after 1,000,000 coin flips. Later, I'll remove that cutoff. We're trying to find the probability of reaching the stop state. Let's call that probability P. I'll place it under the stop state in the diagram. So with probability P, we end with $1. That means the expected money we have at the end is at least P times 1, which is P. On the one hand, the expected money at the end is exactly psi. On the other hand, it's at least P. That means P is at most psi. That's the square root of 5 minus 1 over 2. This analysis was with a cutoff of 1,000,000 coin flips, but the same bound holds with a cutoff of 1,000,000,000 or 1,000,000,000,000 flips. By taking a limit, we get the same bound without any cutoff. Hence, we've shown that the probability of success is at most psi. Okay, let's get back to our previous work. We showed that the probability of success is either 1 or psi, but we just proved it's at most psi. Therefore, it can't be 1, so it must equal psi. Hence, the probability of success is exactly the square root of 5 minus 1 over 2, about 62%. The answer involves the golden ratio. So, if a probability problem looks hard, try building a state diagram. Figure out the relevant states, draw the transition arrows out of each state, label every arrow with a probability, and assign a variable to each state. The picture will tell you what equations to write. State diagrams are simple but powerful. If you like this video, check out this other one too. Thanks for watching!